This is Algebra 1, Term 2, Lesson 11. We're going to be solving systems of linear equations. We're going to be introduced to the idea of linear combinations through an inquiry type task. Kids will solve the systems the traditional way using the elimination method, and we have a 3-act task called counting candy. So let's start with the Desmos activity. So this first task will take the majority of your time, and the first half of this task is really review, but this is your opportunity to see where your kids are and if they truly understand what it means for a point to be a solution to an equation and for a point to be a solution to a system. So you're kind of getting back to the very basic fundamental concepts. So here we're seeing if kids remember or know that a point is a solution if it actually shows up in the graph of the line. So they're going to choose one point as a solution, and then we're going to do the same thing with an equation. Give me a point that is a solution. So we're just basically seeing where the kids are, if they really get the concepts or they've just been memorizing a bunch of processes. So this is a good way to see where their kids are. And here's another one. You should have, once they've done this, it's going to show their point on the line if it's a solution, and if it's not on the line if it's not. So here's where you can gauge their understanding. And then here it's asking them to type in words. What does it mean if I say this point is a solution? What does that mean? How can you check the claim? And so you could use both the equation and the graph to verify that it's a solution. The teacher moves and the sample responses are very good, so be sure you're looking at those probably prior to the lesson to make sure you're getting what you need here. Again, this should be review. If it is review, you'll be going really quickly through this part. But if you discover kids do not know what it means to be a solution, then definitely take the time. You may need a whole nother day on this assignment if you're discovering that. I'm going to go ahead and let you run through these. This one is kind of like a tricky one. Of course it has a solution, but it's not showing. And why is that? So the kids could talk about that and talk about that one. Now here's where it gets interesting. Create two lines that have that solution. They can put these equations in any form they want. Slope, intercept, standard, or just any way. But they're going to solve their system later, so I'm not going to guide them here. I'm just going to let them do what they want. I guarantee you some of these kids are going to come back and change these equations, though, when they get to the end. Because they're going to go, I don't want to solve mine. It's too much. All right, now we're getting into the new stuff. So here we have a balance and the concept of equality. So you may talk about that. We use that a lot in sociology in our social studies classes. We talk about equality. What does that mean? Well, in mathematics, it means for two things to have the same value, same quantity, same weight. And in this balance, it's measuring the weight of two different quantities. And if it's the same, it'll balance. And so here I'm giving them an algebraic expression to put on the left side. What expression could be on the right side? So we're talking about equal or equivalent. Those are all based on the word equal, which expression would match. And then here I have two different expressions. If these are equivalent, and they must be because it's balanced, then what is the value of x? And then it asks them, could you add the 2x and 12 to each side? The knee-jerk reaction here is going to be to say no, because 2x and 12 are different. They're not like terms. But in this particular case, they're actually equal because the value of x is 6. So they need to talk about that. Normally 2x and 12 are not the same, but in this case they are, because in this particular scenario the value of x makes them the same. And then here we have another concept of equality. If the equation is indicating the left side equals the right side, then you can add equal things to both sides. So using the concept of equality, we can add the left sides of these equations and add the right sides of these equations, and they've still got to be equal. I mean, it just makes sense. And I would spend some time thinking about this, because this is the entire idea behind using the elimination method or the linear combinations method, whatever you want to call it. This is the foundation of it right here on slide 13. So stop here and have some talks, get that in our heads before we proceed. Now, this is another thing that's interesting. I never knew this as a student. I was not taught this, but they really should be using graphs to examine their linear combinations. This is a strategy I've actually used with my students when they're solving these, is to open up a Desmos calculator and type in each line as you do the process, because if you'll do that, every single line will intersect the same point, and that is what they're supposed to notice here. So it doesn't matter what you do. If you add the equations, subtract the equations, multiply an equation through by a number, all of the things we normally do to solve using linear combinations, every single line produced will intersect the same solution. And that's actually what we're getting at in this assignment. So this one, they're going to add the last two equations, the blue and the green. So that would be this line and this line. Once they do that, they get an equation, and then they will graph it. Now, I did include the graphing calculator, so if they don't remember how to graph that equation, or they're not even sure what it's asking to graph, then let them look at that, and that's fine. But the goal is to get an equation added to the bunch here, and it will intersect the same point. Same here, they're doing a subtraction this time, so they're going to subtract the first two equations, the red and the blue, so y minus y would give 0. And then be sure to keep the equal sign, then do the subtracting the x's, then subtract the numbers, and then graph that line in the same graph. What is this new equation? What do you notice about this graph? And here they're doing it again. So here's two equations given. Now add the equations and put it here, and it's going to add a line to this graph. And then subtract the equations and put that here, and then what is the solution to this system? Well, they could actually get that here, but encourage them to use these equations to see if they can understand where those might be coming from in the equations. And for 18, we've got a system. Here's the sum, here's the difference. Now you definitely want to paste them on this screen so that they're not going to slide 18 while they're doing it. And then they're going to talk about how you could use these two equations to actually get the solution. So what would you do to these? So I have that discussion here. And then finally, we're going to use the same concept to do this problem. Add the equations, subtract the equations. Can you tell me what the solution is? And then how would you could even talk about it on the last one. How would you get that from what you just did? And then here we're doing it again, sum and difference. Now here's the problem. On the prior problems that they had, by doing the sum, they eliminated one of the variables automatically, and by doing the difference, they eliminated the other variable automatically. Well, here it's going to eliminate one of the variables if you subtract, but it doesn't eliminate any variables if you add. So the question is, what could we do differently for this system? What could we do to figure it out? So hopefully they know to substitute. If your kids have had systems in 8th grade mathematics, and most of mine had, they knew to substitute the variable that they already found in to get the other. So that would be a good time here to talk about that. And here is another one. Let's say I have these two systems. Well, they're not in the same arrangement. How could I rewrite the second equation to get a sum or difference of 0? And so only one of those really is equivalent that makes sense. But I think it says use a sum, so that kind of matters. Be sure they're adding. For this one, which equivalent equation could be used for the second one that would give a sum of 0 for either x or y? In fact, I think both are in here, so they'll need two different answers in this case. And then finally, they're here. Now, this may or may not be plausible for some of your kids, depending on what they wrote for their own system. The ones that got a little crazy, maybe put in a bunch of parentheses, and who knows what they did. So you just kind of have to gauge whether this is going to work for all your students. But it's a great way for them to do something to put in their portfolio, because they created that system back on screen 11. Yes, they do have the same solution as every other student because it gave the solution up front, but they could have their own unique system with that solution. So this would be a good way to showcase what they know. And another thing is you may want to just pause on this one and do the rest of this activity or the rest of this lesson and come back when they've had a little more practice and a little more understanding of the process. So that concludes these 23 screens. That's a lot. Like I said, I've got this scheduled for 1 or 2 days. Probably most people are going to go into day 2. Depending on your kids, though. Like I said, you may fly through that first piece. So we're back at the slides. We've already done our Desmos activity, and this is just a sample of a problem, and it's called, I'm telling them it's called elimination because that's actually the most common name for this process. I've always called it linear combinations, but I believe we use that in vectors and other mathematics, so I guess that's probably not the best thing to call it, but I'm asking kids why the term elimination is a reasonable way to describe this. And so hopefully they notice the bright colored plus 5y minus 5y here and can tell me what's happening. But just have them type some text here to make sense of the directions for the next part. So the next part is taking them to GeoGebra and is asking them to solve using elimination, which is what they just saw, which is also what they were doing in their activity in Desmos. And all they have to do is look down here and they'll have a system. Now conveniently, this one looks pretty good. These I believe are all going to be in standard form, so they're kind of set up for this, and they will solve them. They will need to put their work on a mini whiteboard, or if you prefer they can do it on paper, however you do that. But I usually have my kids write the work on the mini whiteboard. Put their answer here, take a screenshot because it's going to show the 2 lines and the solution once they get this right. If they don't, it'll say try again. All right, the last task after they've gone through all 5 of these is to do a 3-act task, and here they are counting candy. It's a pretty simple task. They don't have to technically use equations to do this one. So this is the counting candy sequel. And so we didn't do the first one, so he recommends, and I kind of do too, you can go back to the counting candy 3-act task. It's very simple. It is not really algebra at all. It's just how many candies would each person get if you had this many. Something really simple. But he does recommend doing it just as to get them into the task. So he says that here. He does have videos, quite a few videos of introducing the problem, releasing some extra information. So this was Act 2, and then they will solve this. You could put all of these images in your slides and not have to use the video for this second piece, but I would. They're all extremely short, 9 seconds, 16 seconds. So it's a fun little task for them to apply what they're learning with systems of equations. And the kids that do this numerically and don't use systems, maybe have somebody who did the system. Can you show me how their method is the same as yours? Even though they didn't write a system, and vice versa. They wrote a system. Can you show me how your arithmetic here is really the same thing as their system? So it's a good idea to kind of marry the two, because we want them to make sense of both numerical and algebraic and graphical methods. All of these are important. This activity helps you do that, helps you bridge that gap. So this concludes solving systems. We'll be doing a little bit more with substitution, but we're kind of wrapping this up. We'll definitely build in some other concepts because we're getting close to the end of the term. I think we have 4 more lessons, so 3 more after this, and then our term exam. So we'll be mixing it all up because the goal is for them to continue to use all the concepts they're learning, to apply those concepts and use them in different contexts. If y'all have any questions, or if you want to share with me some of the things you're doing in your class that go along with these activities, let me know. Y'all have a great day.